Since what we're doing is pattern matching, one of the most problematic pieces about that is you've got to see a lot of patterns. You've got to observe a lot of patterns. You've got to then remember where they were and how to get them from here, so that you have the opportunity to pattern match on your own. Now, fortunately for us, the textbook was rather generous. In the back of the book, in the pages with gray edges, a bunch of reference file pages back here. If you've got the electronic version of the book, they're in the appendix. You should still have access to them. We have a table. Now, the advantage here is that this entire first section matches the set of formulas we saw on whatever page that was, 500, 400, 345, wherever that is, in section 4.9. There's integration by parts right there. Power rule, logarithms, exponentials, change of base formula, all the trigs, the two ugly trig ones that we did in chapter 7, section 2. Here are our trig inverse formulas with sine and tangent and secant. Here are partial fraction decompositions for logarithms. But then there's more. And I mean a lot more. Here's some stuff involving square roots. Now, we can do all of these using things like integration by parts or inverse trig pieces. We can do every one of these. Same thing up here. Here are different kinds of square roots. So all of these are doable with our trig substitution setup. Linear substitutions used in 1,000 different ways. But that means to search through all of this. And by the way, there are about 120 formulas in Mac. Now, before you freak out on me, this belonged to my uncle. This particular book was originally published in 1929, but it is nothing but integral tables. And this particular book has well over 1,000 different patterns in it. So searching through a table doesn't sound like a lot of fun. By the way, those of you in chemistry and biochemistry will see the Chemical Rubber Company, the CRC handbook. They make one for math too. It's got an integral table in it with 780 different integrals in this. I don't want to do this. Up until fairly recently, that was my best bet if I was looking for a pattern I didn't recognize. But that becomes the question. What patterns do I recognize? What patterns don't I recognize? I want to do this integral. I certainly can start trying to play with all sorts of things, but what pattern that we've already seen this semester jumps to your mind, if any? Because I've got a square root with subtraction in it. If I could write that as a squared and u squared, or a squared, normally it would be a squared and x squared, but if I could do a u substitution, make that work, that would be a trig setup, right? Okay, wait a minute. That means this should look like that. Well, let's do a u substitution. Then we'll have something like this. If I want u squared to be 4x squared, then what's u? Yeah? Great. And then du is 2 dx. So this integral turns into square root of 5 minus u squared. I don't have a 2 next to my dx, so I'm going to get a 1/2 du for the dx. I'll put a du there, and I'll put a 1/2 there. What about the top? X squared there. Exactly. What was that, Jacob? If I want to get x squared alone, I've got to divide by that 4. So it'll be 1/4 u squared. So that means I'm going to get a 1/4 u squared. Wait a minute, I have a 1/4 and a 1/2. Let's make it a 1/8. And now I'm primed for trig substitution, right? We know what trig substitution to do. Advantage number 1, I have a formula sheet that tells me whether I should use sine or secant. A squared minus x squared is sine. X squared minus a squared is secant. So this should be sine, which means my next step is to say x is root 5 sine theta. All right. That's going to turn this into a trig integral in sines and cosines, and then I'm going to have to figure out how to simplify that. Maybe I'll need a trig identity. Maybe I'll need a different set of substitutions after the fact, right? This is going to suck, isn't it? In that giant section and table in the back of the textbook, there's an entire section dedicated to square roots that look like a squared minus u squared. So I am going to cheat, 100% cheat. I'm going to say, take a look at these, because that's a squared minus u squared. And which of these resemble this? Where's your book? Ah, 34 has a u squared on top and then the square root a squared minus u squared on the bottom. U squared on the top, a squared minus u squared. Okay, so instead of doing this, I'm going to say I want to use formula number 34. I'm going to write down formula number 34. Minus u over 2, square root a squared minus u squared, plus a squared over 2 times the inverse sine of u over a plus c. Which means somebody already did all that trig work, used the trig reduction in this substitution and left it in A, and came up with this formula already, because there's my sine inverse, which means I must have had theta in here somewhere. And there's this same square root, so I must have had sine of theta in there somewhere. So I must have ended up with the right pieces floating out. Well, now our A is the square root of 5. which means I actually don't have to do the integral. Okay? All right. But that means I can literally go directly from here to 1/8, big parentheses, negative u over 2, square root a squared minus u squared, 5 minus u squared, plus a squared is 5 over 2, sine inverse, u over a is the square root of 5, plus c. I'm 99% done. What's the one last thing I have to do? Say again? Put in the 2x, because that's where I started. Now, you can also take that 1/8 and move it inside, which would give me minus, well, that'll be 2x over 2, right? That's just an x. So I get x over 8, square root 5 minus u squared. Back up to the top, u squared was 4x squared. 5 over 16 here, because I moved the 8 in. Sine inverse of 2x over the square root of 5, close parentheses, plus c. Whew. Wow. What did I short circuit? A lot of trig sub, right? All that stuff from chapter 7, section 3, basically just wash away. Questions? Well, then I have to try and figure out, could I do another substitution to make it square and square? But let's look through that table. Do we see any roots that have fourth powers in them? Because if I do, then I can jump right to those, yes? If I don't, I'll have to try and do something that reduces that power from a 4 to a 2. The bookmark is somewhere for the right section. That's not it. Here we are, table of integrals. Standard first setup. These are all linear forms, squares, linear forms. I got number plus number x to a power where it's any power, right? But this is in my separate book. It's not in the textbook. So I'd have to have another resource, right? Here's one with cubes, c cubed plus or minus x cubed. And then, is there one with fourth powers right after that? I don't know. I have to hunt. Yeah, there it is. Fourth powers. Hot damn. And again, some of these are going to be much more complicated because there are several other substitutions and pieces of algebra that I am hoping they got right. More questions. But do you see my first problem, Nora? I have to know where to look. Do I have a formula that matches this? I hunt for one if I'm lucky. And the second bigger problem, is it right? I can guarantee you, I blew something up because of an error in one of these formulas. A physical explosion occurred because I trusted one of these books in the home. Now, mind you, that particular book was a circuit diagram, and I was putting together a defibrillator rig, and I worked for a pacemaker company for a summer, so I did this setup, and we had to build these testing units for defibrillator leads, and one of the circuit diagrams was wired backwards. I hit the hot side to the ground side, the ground side to the hot side. I blew smoke out of every possible computer chip on that board. Oops. But I trusted the wiring diagram, and it crossed two wires. If there's a sign error in here, how are you going to know? Problem. I have no way of knowing. I can take it on faith. I can hope they got it right, and I can run with it. And 99% of the time, I will. But if it's for something critical, I'm going to double check it. Not just with another table. I'll try and do it by hand, and this problem could be huge. I could be here for a week or more. One of my fellow graduate students at the University of Pittsburgh took his giant differential equations problem, threw it into the computer, and the computer took about 5 to 6 minutes to churn out an answer. This was not a short problem. And so he sat down to check it, and it took him a month. 29 equations in 29 variables involving lots of derivatives. He was there for a while. The formula even in itself might not be enough. What do I want to do this problem?
You want to talk integrating by parts?
I've got polynomial times trig. Integration by parts is the way to go. Yes? Problem. What's du?
Before x cubed.
And v is sine of x, which means when I do integration by parts, uv minus the integral v du have another integration by parts. If I do that integration by parts, I'm going to get another integration by parts. I'm going to have to do integration by parts 4 times to get this problem finished. Back of the book, let's look at the formulas. Trigonometric forms. All sorts of stuff involving powers of trig functions. Chapter 7, section 2. Odd powers, even powers. Sine to the nth. I'm going to get n minus 1 sine with a cosine, and then I'm going to get... This formula results in another integral, just like integration by parts does, doesn't it? Because we took stuff apart different ways. U to a power times sine of u. U to a power times cosine of u gives me the integration by parts piece with the nested next integral. But that means if it's u to the 4th, I'm then going to get u cubed with a cosine, and then I got to go down here and do u cubed with a cosine. I'm going to get u squared with a sine. I keep bouncing back and forth between these two formulas over and over and over again. Now, that's not hard, but it is tedious, right? I can do this integration by parts over and over and over. Okay, but now I've got a minus sign and another minus sign. Minus the integral v du. There's another minus sign. now I've got to distribute all my minus signs. Minus, 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 that's 3 of them, so that's a minus sign. 12x squared cosine x dx. There's my third integration by parts. And now that's similar to the first one because dv is cosine of x, so v is sine of x. So now I'm going to get uv 12x squared sine x minus, wait a minute, there was a minus in front. I need the parentheses. Minus v du integral 24x sine x dx. Oh, cosine of x. Whoops. Copy down the right part. See, my problem is I'm going to be here for a while. I got to do one more integration by parts, but first I have to distribute the minus sign. Maddie, you're looking like I just hit you in the face with a trout. Talk to me.
Why is it cosine?
Because, oh, you're right. I wrote it backwards. Because I said, oh, that one's on the bottom. It must be the one on the top. But I wrote them in the other order. I apologize. Good catch. See, I figured out everything. From there on down is screwed up. Let's not do that. One last integration by parts. U equals 24x. dv equals sine x dx. The antiderivative sign is minus cosine. So I get uv minus the integral of v cosine x du 24 dx. Minus a minus becomes plus. What's the integral of cosine? Hallelujah. X to the fourth sine x plus 4x cubed cosine x minus 12x squared sine x minus 24x cosine x plus 24 sine x plus c. I did the same formula over and over and over and over and still managed to almost screw it up twice. If I have weird substitutions, we said one of the problems with weird substitutions, we may not see what the right substitution is until we're partway through the problem. And that's atrocious. That's a pain in the ass. Nor this one's even worse because under that square root, it's not something squared, it's x squared plus 2x plus a number. That's from here, right? That's the UV. I didn't write out the U and the dV for that one. That's this integration. I'll go back and put it in. U equals 24x, du is 24 dx, dv is sine x dx, so v is cosine x. There's where my cosine came from.
That was just too much, man.
What am I doing? What am I doing here?
Just nasty. Now, I've already primed the pump for you.
I said this one was a weird substitution. And it would be really nice if this would be something squared, wouldn't it? So let's make it something squared. We'll do completing the square.
Could you, I'm not far enough ahead to tell you what, but would you do it by multiplying by 1/1?
It would be much harder to do that multiplying by 1/1. But probably, but I agree with you, I haven't thought through what the 1/1 would be to make that work right. On the other hand, if I do this part, that actually works very nicely. If I write this as x squared plus 2x plus something, what number should go there to make that thing in the parentheses something squared? Hold on, Leo. People process for a minute. Take it, Leo. What do you got for me?
Would be 2 squared.
Unfortunately, no. It's half of 2 squared. You take this number, cut it in half, and then square that.
Okay.
Exactly. It's always, if it's x squared plus bx, the correct number is b over 2 squared. Well, if I add 1 to the problem, I've changed the problem, right? So, Maddie, I'm not multiplying by 1, but I am adding 0. By adding 1 and subtracting 1. Now, that means that that interior of my square root has just become x plus 1 squared plus 3. Hey, something squared plus a number. It's not an x. Let's do a u substitution. And then it'll be u squared. U equals x plus 1. Then I get something squared under my plus number under my square root. If u is x plus 1, then du is dx. So I just get a du there on the end. But what about that x out front? Almost. The u minus 1. And now, this is actually 2 separate integrals. Because I'm going to multiply the square root by the u, and I'm going to multiply the square root by the negative 1, and I'm going to separate them.
Why can you do that?
Why can I do what?
Separate.
If I'm subtracting 2 things, I do the integral of each one, yes? How do I do the first of those 2? Yeah?
Which one to another? U something, the u is u squared. You can say v was u squared plus 3, then the dv would be this 2u, 2v dv, and divide that by 2, you get 1/2 dv.
And I have a u and a du sitting out there. So I'm thrilled to be able to do that. That's a nice problem. What about this one?
That's my trig substitution. Tangent of theta, right? Square root of u squared plus something. If it's plus, that looks like a t. That's going to be tangent. Having written my appropriate comment next to that substitution, I think to myself, what did we do instead of doing the trig substitution earlier? I went to my table. Look for u squared plus a squared under a square root in our table, and lo and behold, that's right at the beginning of our table. Forms involving number squared plus u squared. And that very first one, square root of u squared plus a squared, is exactly what I want to use. So I can use this formula instead of doing that trig substitution. So I can go back over here, and I can write directly below that formula number 21. So that means that this part, pulling that formula, u over 2 square root u squared plus a squared plus a squared over 2 ln u plus square root u squared plus a squared plus c. And to do the first part, that's the integral of 1/2 v raised to the 1/2 power dv. So that's 2/3 v to the 3/2, or 2/3 parentheses u squared plus 3 to the 3/2 minus u over 2 square root of u squared plus 3. Minus distributes into here, makes this a minus sign also. 3/2 ln u plus square root u squared plus 3 plus c. I didn't have to do the trig substitution, but I had to have the formula in front of me to do it. I'm not done. What's left? I got to go back to x. Two-thirds parentheses x plus 1 squared plus 3 to the 3/2 minus x plus 1 over 2 square root of x plus 1 squared plus 3 minus 3/2 ln of x plus 1 plus the square root of x plus 1 squared plus 3 plus c. Holy mackerel. Do any of you know Monty Python at all? My brain hurts. Jesus, that's insane, isn't it? If all I'm doing is referencing a table match for a pattern, looking at patterns and matching patterns is something a computer is really good at. So why don't I give this table to my computer and say what I want you to do is find me the pattern that matches. This used to be fairly expensive. There were specialized pieces of software, Maple, Mathematica, Derive, Maxima, which was spelled M-A-C-S-Y-M-A because it was for the Macintosh, Mac symbolic algebra.
maxima. And all of these people would charge, and right now, if you want to buy a copy of Wolfram Alpha, you're going to pay $1,700 for the professional edition. The student edition is only $150. But Mathematica is run by a guy, put together by a guy by the name of Stephen Wolfram. And Stephen built this. This website, Wolfram Alpha. A little more darkness up here, so we don't quite get as much of a shadow. And now I have to turn the light off. Apparently have to turn the light off. Sorry, people. So you heard that giant shadow and glare over my computer screen. Wolfram Alpha. This particular website is now free, and this does what Wolfram's software does, at least most of it. But what's interesting is it says, enter here what you want to calculate or know. You could write in English. The integral of ln of x, which we had to do with integration by parts. Enter. It did integration by parts. Notice it uses the word log instead of ln. It even tells you that underneath. But that's the correct answer. We wrote x ln of x minus x plus c. We did the whole problem. But if I wanted to write something more complicated, I could use this math input keyboard. And then all sorts of interesting symbols come up. My contrast is wrong. Can we please see the symbol? There we go. Now you can see the symbols. Look, the derivative of roots, powers, fractions, integrals, and definite integrals. So let me pull one of the problems we were looking at just a moment ago. We wanted to calculate that big ugly integration by parts. I'll do that one. The integral of, and notice it puts symbol and the box. So now I have to fill in what goes where, right? It's the integral of, what was our integrand? It was x to the 4th cosine of x. Took us a whole page, right? X, I want a power. So, fix that. Be on the correct side, please. Thank you. I want a power. I'm going to have to use the power button to get the power. So x to the power. I put in the power, and then I write the x in the bottom, and I write the number in the top, 4. 4. I got to get rid of that other x. It's gone. X to the 4th times what? What was our thing of times? Cosine, right? Cosine of x. Oh, and I was integrating dx. We did integration by parts 4 times for this and ended up with 5 integrals total. Not only did it do it, it factored it. It grouped it. All the cosine terms, all the sine terms. That took what, 12 seconds, maybe? It took longer for me to type than it did for it to do it. Every single integral we want to do, I can do here. Absolutely 100% of the time, I guarantee it. If all I want is the answer, I'm done.
I'm going to ask you the same question I asked before. Is it right? How do you know?
I pray to the Almighty Moloch, grant me the knowledge.
No! If I want to know if that's right, I should take its derivative. Take its derivative product will all over the place, and I have to see if it simplifies back down to what I want.
So as much as I have lots of faith in this computer, what it generates for me isn't necessarily understandable or intuitive. Now, here's what I mean a little bit more there, because before I had Wolfram Alpha, I had a copy of Maple and a copy of Mathematica, and they required me to write in symbols. So that first problem right there, INT stands for integral. That says the integral of x squared cosine mx with respect to x. That's the comma x, so that's a dx. Well, that's the first problem we did in the homework for chapter 7 section. That's integration by parts. Twice, and there's my answer. Remember, this is the whole first assignment for chapter 7 section 1. That's the answer. No work. Right? All I do is type in the computer. That's great if you trust it or if you believe that getting the answer is what matters. Here's my problem. Here's chapter 7, section 2, right? Whole bunch of trig stuff, all my trig answers, no problem. I love it. It's working. Here's 7.3. Definite integral. What the hell is that? Arc usually means inverse, right? Arc, cosine, arc. What's the H mean? I got phlegm in my throat. Arctan. H. Technically, that stands for hyperbolic. We didn't do hyperbolic functions. Chapter 3, section 11. I don't know what this answer is. It doesn't help me. Happened down here as well, where I did the inverse sine, but it came out as arc sine hyperbolic. If we were to do that, we'd end up with something with logarithms or tangents, because it's x squared plus 16. That's my tangent, my inverse tangent thing. I should end up with something that makes sense to me. And one of these, I don't think it's on this particular. Oh, I can do partial fractions here too. It'll do all the partial fraction decompositions. So if you're having struggles with the partial fraction decomposition, you don't know what the coefficients are, plug it right in here. I did one of these and I got back the hyperbolic tangent of Ix. We don't do complex numbers. Somebody hands me that, I know they used this technology to get that answer. So one of the problems with relying on something like Wolfram Alpha, which I will completely admit to you, you should use wherever you're allowed to. This entire section of homework is going to ask you to use the tables. Use the tables. Use Wolfram to check them. Use the technology. There's even one problem that asks you to do it both ways. Do it using Wolfram and do it using the table. And see what the difference is. Can you reconcile the two answers?
Honest question. Why are we learning this if we can't use them on an exam?
Okay, for two reasons. The first of which is you are going to go out there into the real world and not everything's an exam question, right? So you should be able to use all the resources in front of you. This is going to be in front of you. As much as ChatGPT is going to be in front of you, as much as whatever the next, Apple just released their comment that their new phone is going to come with the Apple AI built in automatically. The watch, the phone, and the iPad and the Mac are all going to have the AI completely integrated. So as soon as you tell it, I want to start looking at it, it's going to try and finish the sentence for you. It's going to try and direct you to things you meant you were wanting to look at. I hate this. But if I know what it's going to do
I know what I want is something different, I'm going to put that to good use. If I know the technology out there exists to check all this, what am I going to do in the next class? What am I going to do in my thermo class when Dr. Miller asks me to do this giant partial derivative thing that we're going to do in Cal 3? What am I going to do in quantum when she asks me to do this double or triple integral? We haven't even gotten there yet. Some of these integrals get really crazy really quickly. And if all I need is an answer, I'm going to my computer. Last year, I taught DiffyQ for the first time in over a decade, which meant I'd forgotten some of it. So I sat down and retaught myself the pieces I didn't remember. How do you think I checked my work? And not only that, I found and reported errors in the answer key back to the author. Because I said, hey, here's a screenshot of your answer. Here's a screenshot. You've made 2 sign errors, and you've transposed 2 numbers in 2 different places. Please fix the answer key. I'm sure it was, or you switched numbers in the problem that you shouldn't have switched, and this is the latest version. I went from edition 9 to edition 10. Maybe I've got a number that you forgot to change somewhere. This happens to me regularly. Matter of fact, this morning in my other class, I pulled out, I'm using the 8th edition of the book, and I said, ladies and gentlemen, this sentence in the book is wrong because they made a typo in 2 places in this section. When the answer matters, I'm going to trust both my brain and the computer to try and be as close as possible. The fact that you can't use it on a test should matter about that much, because you get to use it in the real world. And honestly, that means the bigger part of this is, can you set it up? Can you see what thing you should be using? I actually had a version of the exam for this chapter that had you do no integrals. I want you to imagine you sit down and I give you a page with 20 integrals on it. You don't have to do any of them. You just have to tell me what method you're going to use and set it up. I gave that exam. I gave it as a homework rather than an exam. I think people wanted to shoot me with a bazooka because it meant, oh, I need this substitution, then it matches this pattern, then it matches this. And that meant they had to have all the patterns so they could get through it in time. Instead of homework, it was in class. It wasn't counted as an exam. It was time. They had no resources, no book, no table, no nothing. Go. Computers are much better pattern matchers than we are. So I'd rather you build some of the lower basic skills than try and jam this thing into your head. On the other hand, the next person who figures out how to do what Neo did, I need to know Kung Fu, and upload it to the back of your head, I'll put this book online in a heartbeat. We'll be done with this class. You got it right ahead. Every time I put that stuff in back, somebody's head to die. I hope you all have a wonderful rest of your day. I will see you all tomorrow.